Every year, over 400 million tons of paper are consumed worldwide. That's more than the weight of all the airplanes ever built by man. But have you ever wondered where this white sheet, on which we write, print, or package goods, comes from? It all begins with raw wood, which machines strip of its bark, shred into even chips, and send to giant boilers, where pressure and temperature transform the solid log into delicate cellulose fibers. This is not just production, it's the alchemy of modern times. And at the end of the video, I will reveal a secret that will change your perception of paper forever. The preparation of raw materials for paper production is a very important and interesting stage that lays the foundation for the quality of all the paper we later get. It begins with bringing the wood into a state convenient for further processing. First, large timber is delivered to the paper mill, where it is debarked. The reason is simple. The bark is not needed. It contains many impurities that spoil the quality of paper and create problems during cooking. To remove the bark, special machines, debarkers, are used. These are large rotating drums or hydraulic systems that, like real tigers, strip the bark from the wooden logs without damaging the wood itself. It's like a thorough scrub for the wood. The amount of bark can reach 15% of the log's weight, so removing it is not just necessary, but it also significantly improves the subsequent process and the final quality. After cleaning the wood from the bark, it is shredded into small pieces, which in the paper industry are called chips. Special mechanical chippers are used. These are machines with a large number of sharp knives that quickly and evenly cut the logs into small chips, approximately 1 and 2 inches long. It's like chopping firewood in half, only on a much smaller scale. It is important that the size of the chips is as uniform as possible. If the pieces are too large or uneven, then during the next stage, cellulose cooking, individual parts will be processed unevenly, which will affect the quality and strength of the paper. Therefore, the chippers are adjusted to maintain maximum stability of the chip size. Immediately after shredding, the chips are fed into cooking boilers. But before that, they are often moistened or slightly steamed to facilitate the softening and dissolution of wood components, such as lignin. These steps also improve the energy-saving characteristics of the process. One of the tricks is that the bark contains various minerals and substances that can contaminate the cellulose, create problems in chemical reactions, and disable the equipment. So, thorough cleaning helps not only to get a cleaned raw material, but also makes the cooking process more stable and of higher quality. Thus, how clean and strong the cellulose mass will be depends on the removal of the bark and the shredding of the wood. To make one medium-sized roll of paper, you need to process several hundred pounds of wood, so every step in the preparation is very important. After the wood in the form of chips enters the huge boilers, it is placed in special reactors, where it is boiled in an aqueous solution of a sulfuric lignin-removing alkali. Most often it is caustic soda and sodium sulfide. Usually, the cooking temperature reaches about 300 degrees Fahrenheit, and the pressure can exceed 15 atmospheres for the process to be effective. The chemical reagents dissolve lignin, the substance that glues the wood fibers together. At the same time, the wood fibers remain practically undamaged, which is important for the quality of the future paper. At the same time, other undesirable components that can affect the color, strength, and texture of the paper are also removed. This process is called sulfate, or craft cooking, and it ensures the production of the strongest and cleanest cellulose among all methods. For different types of paper, the proportions of chemical substances, the time, and the cooking temperature may differ, depending on the type of raw material and the required quality of the final product. After the cooking is complete, the cellulose suspension is cooled, washed to remove the remaining reagents, and sent for further cleaning, removal of residual impurities, and refining. To eliminate the foam that forms during this process, special defoamers are used. After cooking the cellulose, when most of the lignin has already been removed, the paper mass usually has a yellowish or brownish tint due to residual impurities. This is where the bleaching process comes into play. Bleaching is designed to make the cellulose white or as light as possible, which is especially important for printing paper, colored cardboard, or high-quality office products. Most often, Modern chlorine-free bleaching technologies are used, which are more environmentally friendly and do not form dangerous organochlorine compounds. Chemical reagents, such as hydrogen peroxide, ozone, sodium dithionite, or oxygen, gradually oxidize or reduce the colored components, thus lightening the mass without destroying the fibers themselves. In general, this is a fine balance, as too aggressive bleaching can worsen the strength of the paper. In addition to bleaching, at this time, deep cleaning of the cellulose suspension from small impurities, residues of paint, metal particles, resins, which can affect the color and quality of the product, takes place. For this, flotation units are used, where impurities, due to the difference in specific gravity and surface properties, are separated from the mass and removed. After this treatment, the cellulose mass becomes light, clean, and homogeneous, ready for the next stage of forming thin paper sheets. The formation of a paper web is the moment when the cellulose mass, consisting of fibers and water, becomes the paper itself. The process takes place on special equipment, a paper-making machine that has a processing screen. The cellulose suspension is evenly distributed over a large metal screen, which continuously moves forward. Through the openings of the screen, water begins to drain down, reducing the moisture in the paper mass. The fibers, in turn, are retained and begin to form a thin but strong layer. This thin layer, the future sheet of paper, continuously moves together with the screen to a complex of presses and drying rollers. Here, the remaining water is finally squeezed out, the paper is heated, and acquires the required density and texture. After completing these stages, the thin and strong sheet of paper continues its journey to layer-by-layer processing and cutting. After forming a thin layer of cellulose mass, the process of pressing and drying begins. First, the paper sheet passes through the press section of the machine. Here, 2 or 3 heavy rollers press the thin layer, squeezing out the excess water. It's similar to wringing out a wet cloth. Pressing increases the density of the paper and prepares it for the next step. The moisture after the press is reduced to about 45%. Next, the sheet moves on to the drying rollers, large cylinders heated by steam, the temperature of which can reach 300 degrees Fahrenheit. The paper passes between these rollers, and the heat quickly evaporates the remaining moisture. The moisture exits through the open pores of the paper and drains into a condensate collection system. This stage is very dynamic. The paper sheet can move at a speed of several hundred meters per minute, quickly drying, but at the same time retaining its flexibility and strength. After drying, the paper becomes strong, smooth, and ready for further calibration and cutting. If necessary, the sheets pass through calendars, mounted pairs of rollers that give the paper a smooth shine and even thickness. After drying, the paper sheet passes through a pair of large, heavy, and very fast rotating steel rollers. This is called a calendar. These rollers press on the paper with great force, literally rolling it to even out the thickness and give it a shiny surface. The temperature of the rollers can be very different depending on the type of paper, from about 80 degrees to over 500. The heat helps the fibers to melt a little, which improves the smoothness and strength of the web. With the help of calendaring, the paper becomes denser, more uniform in thickness, and also better suited for printing, as the ink lies on such a surface evenly and richly. The final stage of paper making is cutting and packaging. The finished paper roll, or a long ribbon, is fed to automatic cutting machines, where it is cut into sheets of standard or individual sizes, depending on the needs. For this, guillotines are used, large mechanical scissors that make an even and precise cut simultaneously across the entire width. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal, have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum-degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled. The model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold. And the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. The metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions, and the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these 3 products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds: pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies.